this. Okay. Oh. Oh. Okay. The topic of today will be the welding arc. And we're going to start dabbling into plasma physics. Not too deeply, not because I don't want to scare you, it's because I myself don't know it well enough. I'm actually studying quite a bit of it. And one of the interesting things I'm gonna share with you today, a lot of very interesting things, very important things on which we're gonna be building much of the rest of the class. And this will be, will open doors to make numerical predictions. We can make calculations about penetration, about like deposition rate. We can make, we can say what do we expect for voltage and heat input. Many of those things that those who know, and those who don't know, but it's very difficult to anticipate before we try it in an experiment. So this is going to be very useful. That said, many of the things we're going to share today are based in quite a bit of science, but also quite a bit of what I have learned from conferences, from talking with other colleagues. And I already know that what I'm sharing can be better, and I will make it better. And every year is a little bit better. There are a few inconsistencies here and there, but this material here, on which we're going to base pretty much all the rest of the class, is not in any book. Is not concentrated anywhere. So this is the best I could do to put it together in a way that is useful to us as engineers. Physicists might think this is not a big deal, but physicists don't predict how many pounds an hour you're going to be depositing in your weld. Many engineers don't think about plasma physics, and they look at a catalog and tells you things from a catalog. But if it is not in the commercial catalog, then it gets difficult to make an extrapolation beyond what we did yesterday. You will be in so much better shape. Let's put this class in context. The first few weeks of class, we learned a dictionary. And based on that dictionary, we learn words that we use all the time. TIG, MIG, all those things. Some of you didn't know what those were. Now we use them without thinking twice. It's our language. Then we went from from learning a dictionary to discussing metallurgy. A very, very different thing than memorizing a dictionary, and a discipline that is not as well defined as physics, right? And in which we need to look at microstructures and try to figure out these microstructures, what they look like. I don't know, from my mechanical engineer point of view, it's not all that different from palm reading. But again, without metallurgy, we would have no bridges, no cars, no airplanes. So palm reading or no palm reading, whatever it is, it works and we need it. Today, the class is taking a huge, huge change because we're gonna start talking like engineers, and engineering is the use of laws of nature for doing something useful. Today, we're gonna discuss some of those laws of nature, and we're gonna build on that. So let's talk about the arc. You have seen these slides already on the first day of class, but by then, things were so up in the air because we were only starting. So what we see here is a TIG, the tungsten tip of a TIG welding process. We see the arc. We see the weld pull down here. Here is the base plate. When you see this, now you don't need me to tell you. You know this is thick, and you know what the arc is. And you know that all this wavy thing is because the metal is molten. And if we, and in this image, what is interesting is we have electricity going through a gas. That is not a common experience. Electricity does not go through gases in our everyday life. If it did, we go next to an electrical outlet and it would zap us, and it's not a happy time. But that's not the case. Air is an insulator, except that in welding, the gas is a conductor. And why does electricity go through this gap? We did discuss this, but I want to say it again, and we get a little bit deeper. The electricity goes through the gas because it has loose electrons that carry electricity. In that aspect, the gas in welding, this plasma, this very bright light, this spark, whatever we want to call it, behaves somewhat like a metal. These loose electrons carry electricity. Much like in a metal, the outer electrons carry electricity. Now, why are these electrons loose? Why are the electrons loose? And the reason is it's because the plasma, the arc, is very hot. And we did discuss this. How hot? 20,000 Kelvin hot, give or take. If you want, you can call it 10,000. In helium can be even more than 20,000. That sounds like a big number. But when we put it in context and we compare with the surface of the sun is 6,000 Kelvin. Now we really confirm this is a big number. It's like 3 times hotter than the surface of the sun. And the surface of the sun gives us this light that is white. And at these really high temperatures of the arc, the spectrum moves into shorter wavelengths. Those who took the heat transfer class with me might remember towards the end we discussed radiation and how at higher temperatures, the wavelength is shorter and shorter and shorter. And sure enough, at 6,000 degrees, we have white light. At 20,000 degrees, what we have is blue and ultraviolet. And that's why the welding, when you see somebody weld, the light of welding on a wall, it looks bluish because of this high temperature. And that's why if you have a piece of skin exposed, you're gonna get a rather fast tan because you get the ultraviolets of a week in the few minutes of welding. So very hot, very hot. And because it's so hot, it's like shaking an apple tree. If you shake it enough, the apples will fall. And temperature is kinetic energy. That means the atoms are being shaken and they are gonna lose electrons. And those lost electrons are what become the conducting particles in the plasma. Why is it the arc so hot? The arc is so hot because it has a resistance and acts as a resistive heating, right? So as the electrons want to move, they hit the ions and they transfer energy one to the other, and the electricity experiences a resistance. So as we try to push the electricity through this resistor, which is the arc, energy is generated. That's the one source of energy of the arc, right? This resistive heating that gives generates lots of energy of the order of kilowatts and dissipates much of that as radiation. In addition to the heat, electricity causes motion. We did discuss this, but back on the first day of class, we were wondering what the hell we're seeing. Now you see, this is our TIG arc, and the TIG arc is generating an arc. And what I superimposed here comes from numerical modeling that my friends and I did when I was doing my postdoc, still back in Massachusetts. And what we see here is these arrows. Oh, I should annotate here. What we see here is these arrows, and the bigger arrows indicate faster speeds, right? That indicate a plasma jet, right? And this is very interesting because there is no pump, there is no mechanical device here to create a jet. However, without going too deep into this, I can tell you this. The electricity, that is going from positive to negative in this direction, creates a magnetic field. So if the electricity moves in this direction, and I used my right hand rule, some of you might have had electromagnetics, some of you might not. Those of you who don't, please take me on faith. And the electricity generates a magnetic field that goes around the direction of the current, right? And I use the right hand rule, and it goes in the direction of the fingers. And when the electricity is more concentrated, like near the electrode, these magnetic fields are tighter, therefore stronger. And when we are near the plate, these magnetic fields are broader and therefore weaker. Now, there's another interesting thing. Those of you who have taken electromagnetics, you know that electrical current coupled with magnetic fields originate a force. Everybody knows that force because that's the force that makes electric motors work. Those of you who did not take electromagnetics, you know the motors. So I know you have to believe me. And the way this force works is using the cross product that you might have be so glad to have forgotten, but cross product says current times magnetic field, right? Current was going this way. And if it is the magnetic field is going around, times magnetic field gives me, in the third axis, this force that is perpendicular to the current and the magnetic field. This force points to the inside. And this force that points to the inside creates a pressure. And because here the magnetic fields are strong, the pressure is high. And down here, because the magnetic flows, or the magnetic field is low, the force is low and the pressure is low. And we have a differential of pressure that creates a jet without any mechanical device. It's quite amazing. This tighter jet, right, has a velocity. What is the velocity of the tighter jet, of this jet? In welding, is of the order of 300 meters per second. This plane here flies at about 240 meters per second. What means that our weld is hotter than the surface of the sun and faster than a jet plane. And that's what you have in your hands. And it works by a miracle of God with mild steel. But when you're trying to work with more sophisticated materials, or when you're trying to work with different processes, the miracle of God doesn't work so well. And if you want to invent new things, if you want to take advantage of the technology, we need to, at the very least, be conversant on what's going on. And that's what the conversation we're starting here today. So I had discussed to you, like, to understand this combination of magnetic field and electricity, you need to use this field called magnetohydrodynamics, and for which the guy who started the field got a Nobel Prize in 1970. We're not going to be doing like crazy math, but please know that the concepts we're using, they come from there. And welding, we can weld without knowing how to read and write, but understanding welding takes some effort. And I took most of the effort in trying to put things together to explain them to you as clear as I can. These fast plasma can have crazy effects. This is called humping. I took these photos. These are part of my PhD thesis. And these welds that, of course, would be a reject. You'd never see welds like this. because welds like this never see the light of day, right? Like they get trashed. They are all a consequence of this fast plasma we were talking about. You don't know what you're doing, you can end up with this, and making decisions how to deal with this that might not be the optimal decisions. All right, so we are now at the arc, and let's discuss what this welding arc is. Here on the left, I have a MIG arc, and on the right, I have a TIG arc. And those of you who know welding would say they're so different. The only thing in common is the bright light. But if we look at these two very different processes from the point of view of fundamentals, we're gonna see that they share so many similarities in which we can study them. Like much of what we learn from one can be used for the other. For example, this bright light that we see in both arc welding, in all arc welding processes, this comes from the light of the plasma in the column. We have an arc column. In addition, the arc in welding has two more parts for a total of 3 parts. The arc column that gives us the light that we see, then one positive electrode that, the word electrode in welding is tricky. Electrode means whatever we're using in the torch, right? This is an electrode in MIG, and this is the electrode in TIG, right? But in addition, I will use on occasion the word electrode to represent a surface that carries current. For example, in this case, the plate. We call it the plate all the time. But let's be aware that because the plate conducts electricity, it is an electrode in this electric circuit. So we have a positive electrode in MIG, everybody would agree, and we have a negative electrode in TIG, and then the plate is a positive electrode in TIG, and the plate is a negative electrode in MIG, right? Positive, negative, that's unavoidable, right? And these 3 parts of the arc are the key to understand what's going on, and are the key to understand issues like effect of variable polarity, effect of changing polarity, effect of increasing current, increasing arc length. All of those things that are everyday questions will be able to give very good estimates based on this understanding. So the arc, whether it's MIG or whether it's TIG or whether it's subarc welding or whether it's plasma, always has these 3 important parts: the column, the anode, and the cathode. Let's discuss them. Oh, before we discuss those, column, anode, and cathode, let's talk about what plasmas are, right? So a normal gas, whether it's air or can be argon, which is inert, or can be a hydrogen that is diatomic, for example, in 6010 electrodes or 6011 electrodes, which are both cellulosic, when they burn, they generate a lot of hydrogen, H2. Or you can have molecular gases, like for example, if you're doing MIG welding with pure CO2 or argon CO2 mixes. Those are the gases we put, but in the temperature of the arc, they dissociate, right? So the argon can lose an electron, and all of a sudden we have a positive, huge argon ion and a very small and fast negative electron going around. And if we are very, very, very hot, this argon ion might lose a second electron, right? And sometimes you get to see in argon, for example, that if you are too hot, you start to see this second ionization. It's not that common. Diatomic gases like hydrogen, I needed to say something here, that is, as argon and the electron part ways, right, to become an ion and an electron, there's an energy associated with that, not dissimilar to the energies we would put into phase transformations in metals. If I want to vaporize a metal, I need to put a latent heat of vaporization. So in ionization, we have something similar. It's not called latent heat, but there is an energy associated with the transformation from inert argon to argon, ion, and electron. And this energy affects, for example, things like specific heat. In diatomic gases, we have something that is very similar, but there is a small difference. And the small difference is that in these diatomic gases, often they break the molecule before they ionize. So they go from gas like hydrogen, or could be oxygen or nitrogen. First, it's going to dissociate into two atomic hydrogen atoms, which are not necessarily ionized. And then as the energy keeps coming, it might ionize, right? And oh God, this slide has something terrible here. Well, I want to be clear that hydrogen doesn't get a second ionization. So, molecular gases also dissociate, and these dissociations involve energy, right? Involve energy that is absorbed in the arc. Something that I also would like to discuss is the concept of LTE and non-LTE. LTE stands for local thermodynamic equilibrium, and non-LTE means like something there is not this thermodynamic equilibrium. What is a local thermodynamic equilibrium? Local thermodynamic equilibrium means the electrons are hitting the ions, hit the ions in such a way that they share the energy, and the temperature of the electrons measured from their kinetic energy is the same temperature of the ions measured from their kinetic energy. And these temperatures are the same. That's why we call it thermodynamic equilibrium, which is a term that we also use in our heat transfer class, right? And they say local because in other parts of the arc, it might not be in thermodynamic equilibrium. But in this one part, in which the electrons and the ions can share their kinetic energy, we have thermodynamic equilibrium. Now, there are cases in which we don't have this local thermodynamic equilibrium. One of the cases is at very low pressures, because at very low pressures, the atoms start to get farther and farther apart from each other. And when we ionize them, now the ions and the electrons are not going to be interacting, sharing energy efficiently as at higher pressures. So in that case, at low pressures, the electrons are moving freely and crazy and fast, and we can assign a very high temperature to those electrons that are moving freely. But the ions don't move very fast, right? And we would assign for the ions a lower temperature. And now it's very interesting because at the same point in space, we are assigning two different temperatures. It took me a while to wrap my head around this, right? At one point, you're used that whatever you look with your eyes, you can, if you see it, it has one temperature. But if you look at a welding arc, you could see a low pressure welding, a low pressure plasma has hot electrons and cold ions. At what pressure this balances out more or less? Just around 1 atmosphere. Look, in this case, the temperature of the electrons is high, the temperature of the ions is low, and around 1 atmosphere, they become 1. The column of the arc is at 1 atmosphere and in this condition. I want to share with you something that is quite interesting. When I was a professor in Colorado, we did an experiment, which in retrospect, I wish I had done different. What happened? We saw that on Mars, the atmosphere is pretty much pure CO2, which is a welding gas. So we thought, okay, how about if we are welding in space, and instead of using an electron beam as if we're in outer space, but we're welding on Mars, we use the CO2 of the Mars atmosphere as a shielding gas. I thought I was so smart. A group of senior students chose this as a senior project, right? And super smart kids. One of these ended up at MIT, guys with good hands-on skills. And we went and did it. And the atmosphere in Mars is about 0.6, the pressure of the atmosphere on Earth. Well, we had to go to the mining engineering department to get into a vacuum chamber, to evacuate it, put CO2 at that right pressure. And then we tried to run the weld. And guess what? It didn't weld anything. And instead, the cables were glowing blue, right? Was terrible. It didn't work at all. Now, at the time, it was pretty disappointing. Now we know well what happened, and it's something that was known for long. And it is that at the low pressure, that is this pressure that we have in the line of Mars, the plasma would not be in local thermodynamic equilibrium. The plasma would have very cold ions and very hot electrons. Now, the ions are big and the electrons are much, much, much smaller. Does anybody have a thought about what the effect on heat capacity is? That the electrons have a high temperature, ions are cold. What do you think a plasma in these conditions, what the heat capacity do you think it would be? High heat capacity with hot electrons and cold ions? Low heat capacity, what would you expect? The heat capacity is actually low in this case. Exactly, low heat capacity. The electrons are hot, but they have an infinitesimal mass, very little mass. To some extent, electrons would be like getting the head of, get a little pin and heat up the head of the pin red hot. But how much heat is in there? Not very much heat, very little. And those are the electrons. They're like little mosquitoes. Now the ions are like big elephants, but they are all sleeping. Not much is happening. You know, you are familiar with this type of plasmas because that's what is in a fluorescent tube. In a fluorescent tube, we have 0.3% of the atmospheric pressure. And then if we can run a current, we have this thing called the glow discharge, right? In which we can run a current through the electrons, but the fluorescent tube doesn't get really hot because the ions are cold, right? And this discharge, the fluorescent tubes have this fluorescent coating that is what captures this radiation from the electrons and then gives the light we see. Isn't this interesting, right? Like much the same as what was happening in our experiments of welding on Mars. And something on which we are familiar. We have fluorescent tubes all the time. So now that we discussed this LTE, local thermodynamic equilibrium, I want to point to something that is so awesome. The column is more or less LTE. If you talk with a real physicist, they would say it's not really LTE. And I go, yeah, whatever. If it is 99% LTE, I'll take the money and run it. I'm happy with that. I'm an engineer and I need to make something, not just arguments. Now, the anode and the cathode of the welding arc, those are non-LTE. You might wonder, so what? Why do I care? And my answer to that is you care a whole lot because this non-LTE situation is what gives a special voltage in the electrode that melts the electrode, and it's what gives a special voltage on the plate that melts the plate. And this is the key of understanding polarity, current, effect of fluxes or gases. So many things which are so seldom explained, even in commercial literature or in books or even in papers, right? The pressure in welding is more or less 1 atmosphere all over the place. The reason we have non-LTE non-LTE situation near the electrodes or near the electrode and the plate is that when we are very close to a surface, the plasma loses its equilibrium and in what is called a sheath around, and a pre-sheath around these electrodes. And in those parts, despite being at 1 atmosphere, they are not in LTE. And that has very important practical implications. Before we get into the plasma, let's talk about how the electrodes work, right? And the electrodes have something called the work function. And the work function is how much energy does it take to take an electron away from a plate, from a metal, right? In this case, we would have an electrode that has a crystalline structure, whether it's tungsten or is might be molten, doesn't have a crystalline structure, but still is condensed matter. All the atoms are close to each other and they have bonds. And of these bonded atoms, I am going to steal an electron. That is what is called the work function. And these are the electrons that start to circulate in the plasma towards the plate. We would not conduct electricity if we cannot steal an electrode from a cathode, go through the plasma, and land that electrode in the cathode. This energy matters a lot because it's closely associated with the voltages we're going to be seeing in welding. And for the common materials in welding is 4 to 5 volts. And I put a list here of work functions of different materials, different electrode materials. And remember, when I say electrode, I mean whether it's the real electrode or the plate, right? So whether it's MatE or TIG, I'm not going to worry about that anymore. And we see that materials like iron have a work function, aluminum, another work function that is quite similar, tungsten, right? Very, very different things. And in all these cases, to lose an electron to get into the arc, we need about 4 to 5 volts. I want to bring up a very similar concept, which is, but has a quite different implication. Let's talk now about the ionization energy. We saw this exact same graph when we were talking about fluxes. And ionization energy is how much energy it takes me to take an electron away from an atom. Sounds like I'm talking the same as work function. What is the difference? In work function, the atom is part of a condensed matter in which there is bonding between the different atoms, whether it's a crystalline lattice in tungsten or the molten steel in a MatE electrode. But they are together, and I'm stealing an electron from these bonded atoms. In ionization, I'm going to have an unbonded, alone atom, and I'm going to steal the electron from that unbonded atom. Clearly, these two properties are somewhat similar and related, although the final number is different because the bonding energy affects how much energy I would need to steal the electron. In the ionization energy, what do we see? Well, we see that the materials in the first column of the periodic table, those that tend to have 1 electron in the outer orbit, they have low ionization energy. It kind of makes sense because if they lose this electron, they would resemble the electronic configuration of the nearby noble gas, and the elements, for example, fluorine or chlorine, that have 7 electrons in the outer orbit, typically they want an extra electron. They don't want to give an electron. So they have this high electronegativity, and these are difficult to ionize. And those that are like noble gases, in which they are very happy with their electronic configuration, they have the highest ionization potential. And we already discussed how, for example, sodium and potassium have like a low ionization potentials, and they are called arc stabilizers, and how potassium, that has a lower ionization energy than sodium, stabilizes the arc well enough to allow the use of AC, cheap power supplies, in 6011, which we could not do with the 6010 electrodes that have a sodium coating, right? So what have we discussed so far? That everything that is arc welding has an arc with 3 parts: column, anode, and cathode. We also discussed how in the column, like the electrons and the ions are hitting each other in such a way that all the temperature is uniform in the arc column. But in the anode and the cathode, very next to them, and by very next, I'm talking about nanometer scale, there is, the plasma is the organ of tens to hundreds of microns, the tens to hundreds of microns. The plasma is non in this LT, non in equilibrium, which has implications. Then we looked, okay, given that the plasma conducts electricity, we need to put electrons in that plasma to conduct. And the electrons would come from the electrons would come from the electrodes, and there is a potential associated with stealing that electron that is called the work function. And inside the arc, we have the, and inside the arc, we have this, we need to take the electrons from the shielding gas, the gas in the arc, and also there is a voltage and energy associated with stealing the electron from the outer orbit of these gases. What does high ionization energy mean? So high ionization energy means higher voltages for the same arc length. For example, helium will have higher voltage than argon. Yeah, I get to see helium has a high ionization energy compared to argon. It's also going to give, and we have done these experiments in subarc welding, if we use like calcium fluoride fluxes compared with oxide fluxes, the calcium fluoride fluxes have higher voltages for the same arc length, and we could measure the arc length. And look at this, of course, makes sense. Here's fluorine, and here's oxygen. So it makes sense. Higher ionization potential give us higher voltage. And in this case, look at this. Just by looking at the composition of the flux, I would be able to start inferring for that weld, I need to have a higher voltage. Otherwise, I might have like some episodes of short circuit. When TIG was originally developed, was developed to weld aluminum, and aluminum sucks up the heat very fast. So they wanted to use a shielding gas that would generate a lot of heat. What did they use? Helium, and that's what was originally called heliarc. Right? Now we say TIG or gas tungsten arc welding, but originally it had a brand name, heliarc, for the helium. What does low ionization energy mean? Low ionization energy means the arc will be stable, easier to start. I'm discussing potassium and sodium we just did, right? And we would know this straight from these ionization potentials we discussed. Let me show you something about the plasma that might come in handy to understand. This graph on the left is a graph of electrical conductivity at different temperatures. The vertical axis, what the units are don't matter all that much. But in the horizontal axis, we have Kelvin. Look at the scale. 5,000 Kelvin, 10,000 Kelvin, 25,000 Kelvin. Huge, huge, huge temperatures. Here is the surface of the sun, around this temperature here, right? And what do we see? We see that at low temperatures, room temperature would be right here. We see that at room temperature, electrical conductivity is 0. And that is what keeps us safe when we walk next to an electrical outlet. When we heat it to about 7,200 Kelvin, conductivity starts. And the hotter we are, the more conductive it is. Of course, the hotter we are, the more electrons are going to be loose. And my electrical carrying capacity is higher. Here we have a different graph that has the same horizontal axis with the same huge temperatures, but the vertical axis is the radiation losses, right? And when those of you who took the heat transfer class might remember radiation coming from surfaces. I made the point then that we are talking only about radiation from surfaces, but radiation can come from volumes too, right? And when in the arc, each volume of the hot arc is emitting light. And what do we see? That the gas is pretty dark or transparent, but it's not emitting light until about 10,000 Kelvin. And at 10,000 Kelvin, it starts to emit light. 10,000, 11,000 Kelvin. So when you see the arc, what you see is more or less the isotherm of 11,000 Kelvin. It's more or less that what you see. However, electricity is also conducted a little bit outside that, which is not, electricity is conducted at this, in this range too, in which we don't see the light, but electricity is going on. You see that this is kind of, has like these little squiggles, this curve. What are those squiggles? Those squiggles are related with the ionization. So same horizontal axis on the graph on the top right, very large temperatures. And what do we see? This is specific heat on the vertical axis. This curve looks very much like a heating curve in a metal. So we have a specific heat at relatively low temperatures. When we have a phase transformation, the specific heat is high because we have some amount of latent heat involved. And in the case of the arc, we have a similar thing. The phase transformation in this case is ionization, pure argon to argon ion plus an electron. And this hump here is associated with this first ionization. And then the specific heat goes back to be kind of normal and then goes back up again. Why? Goes back up again because it's now starting to lose a second electron at really high temperatures, right? Here is what we see is the specific heat starts to climb to really high levels as we get the second ionization. Because welding is more or less 20,000 Kelvin, we seldom care about what is happening up here, but it's good to know. So there are other properties. I'm not gonna spend much time on this. They're all useful and sometimes cause us like some headaches if we want to do modeling. For example, if you want to model the fluid flow in plasmas, which we are, what viscosity should you choose? Should you choose this low value of viscosity, this high value, this other low value again at high temperatures? Very interesting. Okay. I've been talking a lot about plasmas in general, and it's quite abstract. What the hell does it have to do with grabbing an electrode and starting to weld, right? Has a lot to do, because in our procedure, in our procedures that we need to welding procedure specification, often we have to say, well, we use this voltage and we would have this heat input, and if the voltage varies more than a certain amount, we might need to requalify. What is this voltage? So this is a really, really important thing. In welding, we measure one voltage, right? The machine tells us, these are your volts. But that says very little, because the voltage is distributed over many parts of the welding machine. There is some voltage fall in the cables, which we'll see later. There is some voltage fall in the torch, which we will see later. But I want to focus in the biggest component of voltage in welding. That is the voltage in the arc. And the voltage in the arc is non-intuitive. I'm going to explain this to you, and for you will become second nature. But most people, so if I have an arc of a given length, say I have an arc of 10 millimeters and say 10 millimeters and 24 volts. What would be your guess for a voltage at 5 millimeters, for an arc of 5 millimeters? So 10 millimeters, 24 volts, 5 millimeter arc. Anybody wants to venture a guess? Well, okay, right. So one of the guesses is about half the voltage. But here's the super interesting thing. The voltage in the arc is not proportional. The overall voltage of the arc is not proportional to the arc length, right? And this is very, very important to know. And let's see, the voltage in the arc has a big fall near the anode and a big fall near the cathode, right? And then it goes more or less linearly between over the column. This thickness here that I have here is of the order of 100 microns. This thickness here is of the order of 100 microns. But the arc, 100 microns is 0.1 millimeter. But the arc can be 10 millimeters, right? It can be 100 times that length. This part is proportional. But this part that is near the electrodes has this very big and very fast voltage drops, right? And you get to see that I made it go a little bit up before it comes down. I'm going to discuss this in a minute. But the take-home message of this slide is that the voltage in the arc is not proportional to the length, but instead is made out of three parts, the voltage in the arc. There is something which we're going to call the anode fall voltage, something we are going to call the cathode fall voltage, and what is in between those two fall voltages, that is the arc column. The arc column voltage is more or less proportional to the length, but that is only part of the voltage. We have the anode fall and the cathode fall. So let's start talking about the column. The column was in LTE, electrically neutral, which means from the point of view of modeling, it's not so difficult. And we are hoping with our efforts in the lab that at some point we should be able to predict the effect of having different shielding gases or different fluxes. We should be able to make engineering predictions of what effect is going to happen on the weld. The arc is also what is called transparent to radiation. So that means if I have the arc and the center of the arc is at 20,000 Kelvin and is radiating a lot of heat. This heat goes through all the other parts of the arc as if it was transparent, right? So that's why we're talking by radiation per unit volume, right? And not radiation per unit surface. So the arc is transparent to radiation. Most of the radiation is in the ultraviolet because it's these very high temperatures. The energy balance in the electrode is Joule heating creates is what supplies the energy, and the energy goes out by radiation or by advection. Those of you who took the heat transfer class would remember when we talked about advection, that is the transport of heat by motion, right? You can call it convection if you wish in this case too, right? And different parts of the arc have different balances. The voltage loss in the arc column is one of those things that is convenient. Didn't have to be like this, but it is like this. And it's more or less 1 volt per millimeter for TIG, the TIG arc, and more or less 0.8 volts per meter, 0.8 volts per millimeter for MIG, right? These numbers, right today, I cannot give you a derivation and I cannot give you lots of specific experiments, but there's agreement in the community that these numbers are more or less right. So right now, you would know this, that if you have a 5 millimeter arc in TIG, you have at least 5 volts in the column alone. And if you increase in TIG this to the arc to be 6 millimeters, then you would have increased 1 volt in that arc. There's something interesting here that I didn't put it, or did I? No, that I didn't say explicitly. But voltage in the column, and we're gonna see it both for the anode and the cathode, is more or less independent of current in normal conditions. Is it exactly independent of current? No. I claim it's independent of current, can I make really good predictions? Yes. So in this class, we're gonna be discussing the voltage in the arc column, in the cathode and the anode, as if current did not play much of a role. So when I say in MIG, we have 0.8 volts per millimeter, that would apply to 100 amps and to 300 amps. Okay, that is not exact, and it would not apply if you say, how about if I weld at 1 amp? No, the 1 amp is a very different thing. But for normal conditions, we don't need to worry much about the current, but yes, about the length. Something else very interesting about the arc, both for MIG and TIG, and is that the diameter of the arc is more or less proportional to the square root of the length of the arc. So the arc has this kind of bell shape, and it's not like a cone, it's like a bell. So if I increase my arc length, the diameter of the arc is going to be broader. But if I increase my arc length, say by 20%, I increase my arc length by 20%, the diameter is going to increase by more or less 10%. And this is good to know, because if we have a bead that is too narrow and we want to make the bead wider, one of the things we can do is increase the voltage such that the arc length is longer arc length, and then the diameter of the arc is going to be broader, right? And now we can even anticipate by how much we should do that. If you look at old exams, you're gonna see worked out problems in which we put these formulas to good use. And all these old exams are uploaded, and for all of those for which I have an answer key, I uploaded the answer key for you to check it. We just talked about the arc column. Let's talk about the anode. So in the anode, the voltage fall in the anode is more or less independent of current, as we have been saying for all the parts of the arc voltage in the arc. The current density in the anode depends on the gas. It's more or less 100 amps per square millimeter, approximately. It's not an exact number. In MIG, near the electrode, at the tip of the electrode, most of the gas can be metal vapors because the droplet gets hot to near the boiling point. If we start to use CO2 in MIG, for example, the current density increases. And nobody knows why. We're working on that. But it's a fact that the anode in pure argon has a given size. And if I have more and more and more CO2, the anode gets narrower and narrower. And if you remember when we discussed MIG, and we discussed metal transfer, and we discussed globular versus spray, right? This is very, very connected to the size of the anode in the arc. And the reason with CO2, we cannot get, with pure CO2 or high values of CO2, we cannot get spray transfer is exactly because of this small anode that is caused by the CO2. I know that I cannot get globular, I cannot get spray because I have a small anode with CO2. That I know, everybody agrees. What we don't know is why the anode gets smaller with CO2. We're working on that. So this is a slide that is quite approximate. The bottom line is good and useful. What I'm discussing here is how much energy gets into the anode. In the case of MIG, the anode is the electrode, right? And the amount of heat that comes into the electrode gives me deposition rate. In the case of TIG, the anode is typically the plate. And the amount of heat that goes into the plate gives me penetration. So if I understand the anode, I can start saying very powerful things. So let's try to understand the anode. The anode receives an amount of heat that is given by these two components. One is heat from the arc, for example, the radiation of the arc, that is very little, or because the droplet is immersed in this very hot gas, we would have some amount of heat conduction or convection from the hot gas into the droplet. These two aspects I put in here are not very big. What is big is that we have an amount of heat related with the anode fall voltage. So in this class of today, I will be assuming that the fall voltage that we measure to eventually give us a voltage that we read on the display of the machine, and the voltage that gives me a heat contribution, I'm assuming they are the same. They are not exactly the same. And so far, this is working very well. And I'm looking forward, I'm working to trying to confirm that they are like quite close to each other. But we are going to assume in this class that they are quite close to each other because it allows us to do many good things that work very well. And this is not in any book. This is part of what happened from what we learned from all the conferences and our own research that we are putting together. So if you remember, we talked about a fall voltage in the cathode, fall voltage in the anode. This is the fall voltage in the anode. And voltage times current gives me power, right? And this is the power that melts my wire. where does this voltage in the anode come from? Well, look at this. This is quite awesome. One component, this phi, this is the work function. So when the electrons are loose up in the arc and they attach to our anode, they release an amount of heat because it's like a chemical reaction, more or less. We have the anode that might be iron, an electron comes, bonds with this iron atom, and releases the work function energy. This gives us the bulk of heat. Also, we have a component that is, if you remember, the electrons were moving, so they have kinetic energy, which means they have this heat capacity, which is not very large, but it's not zero. And these electrons come to the anode. And now not only they give us the chemical energy of like having bonded back with the atom, but it gives us all the kinetic energy. So this term is the potential chemical energy. This term is the kinetic energy. And in addition, we have this heat from the anode sheath. In the anode, I'm gonna show you in the next slide, we have like a charge imbalance. And this charge imbalance also brings heat into the anode, right? And I put some numbers here, which you do not need to memorize. But the one number that really matters is that this voltage of the anode overall is more or less 4.8 volts for iron in argon 10% CO2, or 4.2 volts for aluminum. We measure them. I know if you put these voltages, you get like wire deposition rate quite well, right? And what is here is trying to explain where this voltage comes from, and why this voltage is so close to the work function. And in addition, if we have to try new materials, if you tell me about welding tantalum, I would go and look for like work function of tantalum and try to start making inferences from those using these formulas here. But these numbers here, I know they work because we measure them. Let's talk about this sheath. I put microns here, but it's submicron, the thickness. What happens, the anode is positive, and we have all this plasma, in which we have these ions and electrons that are loose. And really, right next to the anode, the plasma is, say, 20,000 Kelvin out here, right? We have anode here and deep into the plasma. And here is the plasma at 20,000 Kelvin, more or less. The anode, whatever material it is not going to be at 20,000 Kelvin. The anode is typically 2,500 degrees C for molten steel, could be 3,000 degrees C for tungsten, right? So it's much less. 20,000 Kelvin out here, more or less 3,000 Kelvin in the anode. So what do we have? We have a boundary layer, much like the same as we have discussed in the heat transfer class. And in this boundary layer, we have a temperature gradient for the ions. The ions have a temperature gradient, and the non-ionized atoms. They are slow, they have a temperature gradient. But the electrons, they keep moving, they kind of overshoot this cooling of the ions. And then we have a difference in temperature. We have the ions that are colder and the electrons are hotter. And then very near the anode, the potential, the anode absorbs all the electrons that are nearby. So here we start to have a depletion of electrons, right? And, and in this depletion of electrons, we have a charge imbalance. Let's talk about the cathode. So there are two types of cathode, and we know this. one is called the thermionic cathode. That is the case of tungsten, right? When the tungsten is negative in TIG. And then we have the non-thermionic cathode. That would be, for example, the case of would be the case of the plate in MIG. The plate in MIG is negative and it's a cathode. Okay, so in thermionic is a way of losing electrons that all materials have. All materials can lose electrons by thermionic emission. But here's the catch. To emit by thermionic emission, you need to be really, really hot. So although all materials can lose electrons by thermionic emission, not all materials can exist at the high temperature that is needed. They can melt and they can vaporize. So there are few materials that can have thermionic emission without vaporization. One of those is tungsten. So typically people say that thermionic materials are refractory. And what it essentially means is refractory materials can have thermionic emission without evaporating. And for thermionic emission, we can calculate the current density, how many amps per square millimeter we're gonna get using this formula here. And in this formula here, we have the work function, we have Boltzmann constant and temperature. And this is the charge of an electron. And this is a fairly good prediction for the current density emitting the amount of electrons emitted from a thermionic cathode. Let's talk about the energy balance in this case. In this case, the energy balance is very much the same as before. We have some amount of heat that comes from convection or radiation into the cathode. And then the big part, that is the amount of heat that happens at the cathode fault voltage. And the cathode fault voltage, for the case of all cathodes, in this case, we have a negative work function. And why is this? It's negative work function because when the electron leaves the cathode, it's taking this work function away with it, right? In the anode, the electron comes and brings the work function into the substrate. So in the case of the cathode, the electrons that leave take energy away. They have a cooling effect. Similarly, to give some amount of kinetic energy to these electrons, we need to, this kinetic energy comes from the cathode, and it cools down, it refrigerates the cathode. So these two terms here mean the cathode is going to be losing heat. The cathode sheath, right? That's the voltage fall in which we are going to generate heat. And these two terms more or less balance each other. For the end result is in a thermionic cathode, such as TIG. The fault voltage, this fault voltage of the cathode in the tungsten is of the order of 1 volt, give or take. They're not good measurements for those, but if you put 1 volt, you can reproduce many of the things we see, right? Now, compare this with the anode fault voltage that was of the order of 4.8 or 4.2, right? The anode generates about 4.5 volts of times current, generates quite a bit of energy, and the thermionic cathode, little energy. And you want the thermionic cathode to generate very little energy. Otherwise, you would be melting the tungsten if you put too much energy into the thermionic cathode. And you don't want to melt the tungsten, not all the time. So the voltage fall in the thermionic cathode is more or less independent of current. The current density is more or less independent of shielding gas. So I just switched. I discussed thermionic. I want to discuss now the non-thermionic cathode. The non-thermionic cathode is the case of the plate in MIG, right? Typically, the electrode is positive, the plate is negative. And much like before, this thermionic cathode, non-thermionic cathode, has a voltage fall associated with it that is more or less independent of current. The current density in the thermionic cathode is more or less independent of the shielding gas too. This is not the problem like we have in the anode. We change argon for CO2 and we change the current density very much in the anode. But in the cathode, no, it's more or less the same. In the non-thermionic cathode, the way the electrons come out is because of a high localized electric fields. So there is a very interesting effect that although with our eyes, we see the cathode in welding as if it was uniform with our eyes, the plate looks like as if the arc is coming all even from the plate. In reality, the non-thermionic cathode is like a lightning strike. And the cathode, the non-thermionic cathode in welding, in reality is like a really crazy electric storm in which we have many lightning rays that are going all over the cathode. And in our eyes, we perceive it as something uniform. And these these little local mini cathodes, right? They attach to things that would have higher facility to emit an electron. For example, oxides, right? Oxides help emit electrons, and that's the reason we use for example, 2% oxygen to stabilize the cathode in steel welding, because this little amount of oxygen is going to create some amount of oxidation that stabilizes the cathode, right? This is the reason why, for example, if we put thoria in TIG, the fact that it's an oxide helps lower the work function of the tungsten electrode and help it be more stable and colder, right? And this is why when we are doing TIG welding of aluminum, we use variable polarity for cleaning the plate. We discussed that. But when we change the polarity and the electrode is positive in TIG welding of aluminum, the plate is negative and the plate is a cathode. And the arc attaches to the oxides on the aluminum and cleans it up, right? And this is the mini lightnings that we don't see. What is the overall energy balance of the cathode? So the non-thermionic cathode, this equation looks the same as before. We lose the work function with the electrons that go away. We lose the kinetic energy of the electrons as they go away. And we gain energy through a cathode sheath. The non-thermionic cathode is not very well understood. So people assume some kind of empirical cathode sheath, which we have measured too in our lab. And this ends up resulting in an overall voltage at the cathode of, say, 13.8 volts for argon oxygen in MIG, or 11 volts for pure argon, which would be the case of TIG. Let's think of this. The anode had a voltage fall of the order of 4.5 volts. The cathode, the thermionic cathode, is more or less 1. So the voltage times current gives us power, so lower voltages means lower energy. And in the anode, we have 4.5 volts that help us melt the anode. In tungsten, we have more or less 1 volt that hopefully does not melt our cathode. But then in a non-thermionic cathode, that is the case, for example, of MIG, we have 11 or 13.8 volts in the cathode. That is a lot of energy. We went from a anode at 4.5 to a cathode at nearly 14, right? So there is a lot more energy in the cathode, a non-thermionic cathode, than in the anode. The negative part of if outside TIG, the negative metal tends to melt a lot more than the positive metal. And that's what explains the effect of variable polarity. It explains the effect of flipping polarity. And because the energy is current times voltage, and the voltage is more or less constant, you get to see immediately how the amount of energy you put in is proportional to the current. I have a video here. If you see this video, you're gonna see, this is MIG welding of aluminum, and you're gonna get to see some kind of a shimmer, right? This is 10,000 frames per second. The cathode spots, the little mini lightnings, they happen in millionths of a second. So we're not seeing the lightnings properly, but what you get to see, you see a shimmer. You see that when the current is high, you see a shimmer in this image. And this shimmer, for example, here at the edge of the arc, this shimmer are the roots of all those lightnings that is staying a little hotter, a little bit longer than the lightning. That's why we could catch it with our camera, right? This shimmer are the cathode spots in action. In this class, we're going to assume that the cathode is uniform, like as if it had a constant current density, acknowledging that in reality, that constant current density is the consequence of an electric storm that is so intense that we stop seeing the lightnings and we see just uniform. So in this last slide before we stop, I want to address the issue, the part that is the contribution of the arc to melting. So we talked about the voltage fall in the anode and the voltage fall in the cathode. And the arc gives some amount of energy to the plate and to the electrode. The energy to the electrode, right? We're going to use this formula that is similar to the ones we use in heat transfer. Area times convection coefficient times a delta T, right? And the convection coefficient for heat from the arc into the electrode is more or less 400 watts per meter square Kelvin. It's high for being a gas, but it's quite reasonable. This gives us, let us calculate the effect of convection into the electrode. And then on the plate, we have something that is a lot simpler that I hope to get better at some point, but this is something that gives us good numbers. The power in the arc is current times voltage, right? And for example, an arc of 3 millimeters in TIG would be 3 volts. And if we are running that at 100 amps, would be 300 watts, right? And what we're going to assume is that 1/3 of the arc energy goes to the plate. It would be like 100 watts from that arc goes into the plate. I'm not going to go over this slide, but this is the most important slide that summarizes all these numbers we discussed. This slide is gold. With this slide, I was in Japan, and I was in China solving problems, and I was in the US and in Canada solving concrete problems that they asked me. Once in Japan, it was crazy. I went to a conference and they asked me to go visit a company. And I couldn't say no. They put me in a car, they drove me for an hour. They want to show me a subarc welding operation, and they started to ask me questions about arc length and voltage. And I had to think on my feet, and I used these numbers, and I was dead on what they were seeing. Same with China. They have a big problem of an arc that was being interrupted in subarc welding too. And using these numbers, we could explain exactly what was happening. So I'm gonna stop the lecture here. But if you look at all the exams, you're gonna see how these numbers come together to solve concrete problems. One last thing, I put up the Socrates,